Okay, great. Hello, everyone. My name is Chinmayi Krishnappa. I'm a consulting member of technical staff with the Data Space and Transaction Group at Oracle. I've been with Oracle and with DST for close to 8.5 years now. I want to start off by thanking all of you for taking time to attend this at almost the end of the day, I think, for most of you. On the bright side, like I said, this is a topic that's reasonably light and it's pretty well known. So hopefully we can all just relax and enjoy the session. I'm going to be talking about Oracle sequences. That's the sequence objects in the Oracle database. And we meant for this to be a talk that will cover everything, right from the basics to some recent enhancements that we've made. So a lot of the content may be more than familiar to some of you, but I hope that everyone can find at least something new that they can take back with them from here. Okay. So to start with, what are sequences? An Oracle sequence is basically a database object that acts like a unique number generator, and it follows some user-defined order. Now, the structure and order that a user can specify is fairly limited. For example, you can specify whether it's an ascending or descending sequence, like what's the increment, the step increment, whether it's going to cycle through its range, etc. And they were introduced in version 6. So basically, they've been around for a long, long time. So prior to having sequences in the Oracle database, when end users required unique number generators, what they would usually have to do is find workarounds in the application. And any such workaround would typically involve serialization, either at the transaction level or possibly even higher, say, maybe getting your own application level lock. And of course, a higher level serialization, it would give you perfect ordering, at least as far as the application is concerned. But in general, most applications aren't looking for such perfect ordering. They're generally only looking for a unique identifier and nothing more. And so for this common generic use case, it makes perfect sense to have a sequence database object with the low-level serialization provided inside the database. So it must be pointed out that there are certain things that the Oracle sequence object does not guarantee. As I already mentioned, we don't guarantee commit time ordering. Like even ordered sequences, which are specifically meant to provide ordering across sessions and instances, cannot provide this guarantee. For example, like if you have a number of sessions that are all advancing the same sequence, they will all get their next vals in order, but if they don't commit their transactions in the same order, then you are losing the perceived ordering that the user sees. Another guarantee that kind of sometimes we're asked by customers, but we have to often point out that it's not provided, is that you can't provide gapless values. Actually, if you actually go down to the details of the implementation, the values returned are actually gapless, but what the user experiences is not what the sequence object returns. Because you can have transactions that are aborted, you can have failures, session or instance failures, and even without failures, if you have like a multi-user environment where they're all sharing the same sequence, you will see gaps, because those gaps are actually values that have been returned to some other user. And of course, in a rack setting where you invariably have parallelism because you have multiple instances and sessions, you're going to see this a lot more. So what is a guarantee that the sequence object actually provides is that you can get unique values. Once a value is given out, it will never be repeated. Again, it comes with the caveat that if you alter the sequence in the DDL, then you can have repeated values. Okay, so syntax is something that we can all easily find online, so I'm not going to spend too much time on it. It's fairly simple. You have the create sequence and the alter sequence DDLs. You have a number of attributes you can specify. Common ones that you would generally use are min value, max value to define the bounds. Your increment tells you, how the sequence advances, and the sign of the increment tells you whether it goes up or it goes down. The ones that I've marked in red are the ones that we'll probably look at in a little more detail today. The cache and the order attributes are something that we'll go over in more detail, and those are the ones for which we've had some enhancements made to make performance issues related to them slightly better. The scale, extend, and restart are fairly newer features, so I'll touch up on those as well. So the alter sequence, like I said, pretty much takes all the same attributes as the create sequence DDL. The one exception is restart. And again, like I said, we'll look at this further. So once you created a sequence, using it is fairly straightforward. There's only two operations. There's next val, which gives you the next sequence value, and cur val, which basically gives you the last value that was given out. So how do applications typically use databases sequences? So one typical use is to generate an automatic primary key that gets inserted into a table column. These columns typically have an index or a trigger on them and some constraints. There are certain applications that also require ordering. For example, if sequence values are used to feed into the reservation ID, say, of a reservation system, then you want that a reservation generated later has a higher ID. And some applications sometimes just use it to generate a unique number. This is a less common use case, but isn't unheard of. So, so the cur val and next val that we saw in the previous slide, you can use that in a SQL session to insert into a table column. But you can also use cur val and next val in your application code to insert the value automatically into a table column. And to do that, you can create a table and specify one or more columns as identity columns. So any identity columns are automatically associated with an internal sequence that feeds the column. So you can also qualify them with an always, by default, and by default or null attributes. Always basically specifies that the column value can never be explicitly passed in an insert statement, and it's always picked up by advancing the sequence. On default attribute basically says that the sequence value is used as a default if no value is passed into the insert statement. And the by default or null is newer and specifies, it's pretty much the same as default, but if the default passes in a null, then the null is not inserted, but the sequence is advanced and you use a value from the sequence. So prior to 12G, we didn't have the identity syntax. And so in those cases, you had to go through a slightly heavy-handed approach of having an insert trigger, and then you would associate the sequence as part of the trigger's action. Okay, so the keep attribute is a lesser known one. Developers would never have to use it. It's you would only use it in certain special circumstances. So this attribute relates specifically to application continuity. So application continuity was introduced in 12.1, I believe, and the goal is to give users a seamless experience with respect to outages for their workloads. So basically, you keep track of the affected sessions, and instead of throwing timeouts and errors, you try to replay the workload from the point of failure in such a way that the worst experience that the user gets is a slight delay in the execution. So when we think of how you would replay a workload that involves a sequence, it's easy to see that it's not very simple, because as we've already discussed, once a sequence value is given out, it's never repeated. So just for the sake of replay, the keep attribute was introduced. So if a sequence is altered or created with the keep, then if you're ever replaying a workload, then the same next val will be returned. The default for a sequence, of course, is no keep, and that's what I think most of us would use all of the time. Now, the keep attribute is sometimes confused with the more well-known shared pool keep procedure. This is not limited to sequences. It basically just is used to keep a KGL object pinned in the shared pool. And you can use it for sequence objects that you expect to be hot, and it just prevents it from aging out. So, sometimes the shared pool is not appropriately sized. So if you're in a setting like that, it helps to pin the sequence object in the cache, in the shared pool. And sometimes you just have a busy workload. And even though your shared pool is appropriately sized, if you have a very busy workload, then it could be aging things out of the shared pool more frequently. Okay, one of the most important attributes of sequences is the cache size. So the cache essentially is a way to cache a block of sequence numbers in memory to avoid having to make trips to disk frequently, basically for every next val. So by default, all sequences are cached. and they're associated with a default cache size of 20. This means that an instance gets sequence values in blocks of 20 each time it reads from disk, and sessions pick off of these values in the cache. So like I said, it's a mechanism to reduce how many times you go to disk. The cache is instance local. So if you have a number of instances, then each instance has a different block of numbers cached in the SGA. Now it's easy to see why it makes almost no sense to have an uncached sequence. Even if you intend to use a sequence very rarely, there is no rational reason why you want to make a trip to disk every time, especially when the default cache size is so small, that is 20. So even if you lose 20 numbers, you're okay. One downside to caching is how we recover from crashes. So if the instance goes down, we lose the cached numbers because there's no way to really say how many were used or unused. And so in order to ensure that we're always returning a unique value, you basically have to read a new cache of values from disk. And this is essentially the most important trade-off associated with sequence objects today, basically picking the right cache size so that you're not, you can have a performant workload where you're not going to disk too often. At the same time, you want to keep it small enough that you don't lose a huge chunk of values with every failure. So over the years, we've seen many parallel workloads that use a sequence to populate a table, and they've all required performance fixes where we primarily altered the cache size. And so that basically tells you that the default of 20 is almost too small for any reasonable workload. The other important attribute and a source of performance issues is ordered sequences. And by default, sequences are unordered. And all this means is that there is no enforcement in the order in which next vals are given out. So if you want an ordered sequence, you have to explicitly specify the order attribute during creation or with the alter DDL. So if you have an ordered sequence, there is a strict enforced ordering across sessions that access the sequence. So that basically means if session 1 advances the sequence before session 2, then session 1 always sees a value that occurs earlier in the sequence range than session 2. Now in a non-rack setting, we have a single instance, and an ordered sequence is essentially indistinguishable from an unordered sequence because you're always like the sequence cache is local to the instance, and sessions are always picking next vals from the sequence cache, and they're going to use some form of locking to pick it up, so the ordering is automatically provided. The true issue arises when you have an ordered sequence on rack, because we need to maintain ordering across sessions and across instances. And we know that on rack, we need to go through the DLM for a lock. And if this turns out to be a hot sequence, then this can cause huge performance issues, and as we've often seen with customers. So how do we deal with this? Well, so far, we've usually discouraged using ordered sequences on rack. And this has usually worked because most customers understand that you do need to get a lock for every next val when you're on rack. However, in the recent past, we've had a few cases where customers have been using ordered sequences for a while, and they were not prepared to make the move to unordered sequences. This is despite the fact, like as we've discussed in earlier slides, that true ordering at the commit level is not guaranteed even by an ordered sequence. So we've been actively working on a few ideas to address this contention with ordered sequences, and I'll go over some of these ideas in the coming slides. The last point about ordered sequences is that they're almost always cached. Now, this can seem a little counterintuitive because caches are instance local. And if every next val must be synchronized across instances, it seems that having a cache should not really provide any additional benefits. In reality, it does it does, and this is especially true when the access to the sequence is a little skewed. Like say, you have an active passive setup where there's one instance that's accessing the sequence way more than the other ones. And we'll see how these instance local caches can actually be shared efficiently across rack in a later slide. Okay. So there are 3 primary points of synchronization with sequence access. And again, all performance issues come with one or more of these constructs. Almost all of them have to do with cached and or ordered sequences. So let's dive a little deeper to understand how these work. The first point of synchronization is related purely to cache sequences. This is the sequence latch. And if you're looking at an AWR report, this should show up as KDN LCH on the report. So this latch is responsible for protecting access to the instance local cache. And the second point of synchronization is with the SQ NQ, and this is the NQ that protects the cache replenishment. So cache replenishment essentially is a trip to disk to load a new cache of values once you exhausted your cache. And on the AWR report, this shows up as a wait on the, like I said, the SQ NQ. So the bulk of issues that we usually see with sequences has to do with massive parallel inserts where we're contending on the SQ NQ. You're basically having to go to disk because you're exhausting the cache too often. And like I already mentioned, it's more pronounced on RAC since now we have to go through the DLM. So we've seen a bunch of customers complain about this over the years. And earlier resolutions have usually been, among other things, asking them to just increase the cache size to reduce disk trips. Other things that have helped is, reducing invalidations and hard passes, using the keep to just keep it in prevent it from aging out from the SGA, etc. So usually increasing a combination of these suggestions brings down the problem to some acceptable level. Life goes on for some time before someone runs into this all over again. The third point of synchronization is specific to ordered sequences. And this is because we definitely need a lock in order to advance an ordered sequence. This NQ is SV, and this is how you would see it on the AWR report. So this is an instance lock. And an instance lock is associated with a 16-byte lock value. So the next val is usually written to the instance lock by a session before it's released, and the next session that gets the lock just reads the next val from here, and so on and so forth. So this is almost always a source of contention with an ordered sequence. And you can see how this can become very expensive since you essentially have to get this for every next val. So in general, like I said, we pretty much suggest or discourage using ordered sequences on RAC. And when someone comes up with an issue, we generally first try to investigate whether using an unordered sequence even works for their case. And sometimes increasing the cache size has helped too. Because sometimes with ordered sequences, this is something to remember, is that the contention can show up as SV, but the underlying condition can actually be SQ. This is because all sessions first get the ordering cache. So it helps to see if we can resolve the SQ first. So the cache resizing that I mentioned here is something that's going to be available very soon, and it basically provides a way for you to automatically resize the cache, and we look at how that works going forward. Okay, so this is talking about two recent customer issues that we ran into. While this is specific to two customers, most of the issues that we've dealt with usually falls in one of these two categories. So in the first case, we had a customer moving from a non-rack to a rack setup. They had a 2-node rack set up in active passive mode. They were using an ordered sequence, but given the setup, it was primarily being used on one instance. So this is a case where the contention showed up as SV, but we diagnosed that the underlying issue was actually with SQ. And as was customary, we got them to increase the cache size, and we also requested them to make the sequence unordered. And this brought down the wait time significantly, but however, it still wasn't within the limits that they were looking at. And this was a case where, looking at dynamic cache resizing helped. In the second case, we again had a 2-node setup. And in this case, the customer was moving from on-premise to cloud. This case was interesting because this was a customer that was not willing to get rid of the ordered sequence for historical reasons. They'd been using this for several years and they didn't want to make a change at this point. And so we look at how we resolve this one as well. Okay, so first let's look at how these these locks come into play. Starting first with unordered sequences. So every sequence has its metadata in one row of sequence $. This is protected by the row cache object, which is DC sequences. The high watermark column that you see here is the start of the next block of sequence numbers that can be picked up from disk. So let's look at a situation where we have two instances. Now, every instance has its own instance local sequence cache. In this case, instance 1 has cached values 1 to 20. Instance 2 has cached values 21 to 40. The KGL latch that I spoke about serializes access to the cache on each instance. Now, this latch is usually held for a very short period of time, because most of the work done under the latch is to simply advance to the next value. So it's a very small amount of work. So this is why it also almost never shows up hot on the AWR report. And this is our lowest concerns in terms of a performance issue. Now, if the session gets the latch and realizes that the cache is exhausted, as is the case with instance 2, then the session tries to, let me see if I can, okay. As an instance 2, then the session tries to acquire the cache replenishment NQ. So you will see here that it tries to get the SQ NQ, and then it gets a new cache of values, which in this case would be 41 to 60. Then once the cache is refreshed with a new set of values, sessions can continue reading those values from the cache. Okay. With ordered sequences, we have one additional lock. So again, you have the latch and the SQNQ, but we have one additional lock, which is the ordering or SVNQ. So every instance acquires this in null mode once the sequence is loaded, and it is held in the background by LCK0. So again, we look at the two instance example. Instance 2 is working with a cache of values 1 to 20. Instance 1 is using 40 to 60. So when a foreground wants to advance an ordered sequence, it first gets the SVNQ in X mode, and it writes the next value as per the ordering to the lock value. So in this case, session 3 writes 44 as the next val. Now, when instance 2 acquires this lock, it sees that the next val is beyond its cache. Okay, I think there is some problem with the animation. So this was originally 1 to 20. So it basically sees that, so it sees that the 44 is beyond its cache. So instead of going to disk, what instance 2 does is it knows that the cache size is 20. So it basically adjusts the cache in, cache size boundaries to make sure that this next val falls within an acceptable boundary. So it basically logically is sharing the cache of instance 1. And of course, if the cache is depleted, then whichever instance sees that, it tries to replenish it by getting the SQNQ. So this is basically how all three locks are used. Okay. Now, the first topic we'll go over to address sequence performance, particularly with the SQNQ, is dynamic cache resizing. Now, as the name suggests, the idea is that we would grow or shrink the sequence cache based on usage. Now, this eliminates the need to have to manually alter the sequence cache size through a DDL in response to contention. So users can continue to stick to their default cache size of 20, and the elastic nature of the cache will automatically take care of bringing down contention on the SQNQ. So this requires no DDL changes, and they should automatically be available. Okay, so first let's look at how this works for unordered sequences. So we basically look at how much time has passed since the last cache replenishment and what was the last cache size. So we use these two pieces of information to project how many sequence values we expect to be consumed in the next 10 seconds. So it's basically an estimation based on previous usage. And we believe 10 seconds should be small enough to prevent the cache size from growing indefinitely. In addition to this time bound used for the projection, we also restrict by the scale factor by which the cache size can grow. So every increment is bounded by 10x the previous cache size, and we also prevent it from growing beyond 1 million. And this dynamic cache size is not persisted to disk, so no DDL changes are needed from the customer. And we also prevent the cache size from falling below, whatever was specified with the DDL. So if the default of 20, we would never go below 20, but it can keep growing and shrinking between 20 and, based on usage up to the max limit that's allowed. Okay. So we evaluated the performance of this by comparing it with manually configured cache sizes. So the table on the bottom left is basically without the feature. We manually set the cache size to different values, and we evaluated the throughput. And then, and you can see that, the throughput roughly stagnates around like 20K, a cache size of 20K. We then turned on the feature and ran it with a default cache size of 20, and the cache was automatically, it reached a cache size of 25, approximately 25K, and we matched the throughput that was seen with the base numbers. So this basically shows that we were matching, what you could get by manually setting the cache size. Okay, so what can we do with ordered sequences? So this was not straightforward to implement with ordered sequences. And this is because each instance can have a completely different dynamic cache size. And if you remember, when we looked at how the enqueues work with ordered sequences, we said that the instances logically share the cache of the other instance by adjusting the endpoints of their cache. And this only works when you have these static cache sizes. So if you have dynamic cache sizes, then you can't really do the cache adjustment as easily. So to overcome this, we've modified the SVNQ to now use a much larger size lock. And we not only pass the next val, but we also pass the high watermark. So instances can now directly read the next val as they've always been doing. In addition, when they read the high watermark, they can just adjust their cache to the range between the next val and the high watermark. So once again, for ordered sequences, we evaluated how they perform by comparing with the performance with the manually configured cache sizes. And so this is a little interesting because if you see, the average wait time on SVNQs kind of plateaus off at a fairly small cache size of, like around, somewhere between 2000 and 20K. And after that, we get no further improvements by increasing the cache size. This is because at this point, we're contending purely on the ordering SVNQ. So while we were able to bring down the the weights with automatic caching, there's still a lot that we have to do to address the actual SV contention with the ordering NQ. So if all things go well, interesting solutions to further bring this down. And we're in the process of working this out. Some of the ideas that we are considering is prioritizing local waiters over remote waiters, maybe having one lock holder reserve a block of sequences and values and distributing among waiters. And another idea that we've discussed is, like deferred ping, which is a pretty popular buffer cache algorithm, and we're planning to do something similar for ordered sequences as well. Okay. Now let's look at another fairly recent feature called scalable sequences. The name isn't the most easy to understand exactly what it does, but like putting that aside, it helps to address a different type of contention that's not directly tied to the internals of the Oracle sequence. So this isn't contention on one of the locks. Rather, this addresses contention based on how sequences are typically used in applications. So as we've discussed before, a common use case for sequences is inserting into a table column, and typically with an index on it. And typically this insertion is done with a high degree of parallelism. And since we're inserting increasing values from the sequence, the B plus tree grows at the tail. So we basically have a right growing index here where the last block becomes a hotspot leading to contention. Now, previously, a number of techniques have been tried to overcome contention. One is, you just increase the cache size. Since cache sizes are instance local, where every instance is going to cache a different block. And so you basically get affinity of leaf blocks to instances by doing that. Another idea that's often used is to use a reverse key index where the bytes of the index of the key are reversed. And so this basically helps to spread the heat from a single block to many to many cold blocks. Using a, like partitioning the index is another idea. Unfortunately, all of these techniques, they work, but they come with their limitations. For example, a large cache size does not help in a non-rack setting. A reverse key index is great, but by exchanging a single block for multiple cold blocks, we're basically increasing the number of physical reads for the same number of inserts in the workload. And finally, again, a partition index doesn't help to affinitize blocks to in a rack setting, so you don't get instance affinity. So what we'd like is a solution that works for both single instance as well as rack settings. So we want leaf blocks to be affinitized to instances, and we also want leaf blocks to be affinitized to processors in a non-rack setting. And we want to have all of this without application changes or having to create another index or having to alter an existing index. The solution we have in place today works as follows. The sequence next val is prefixed with a 6-digit numeric offset. Now, this is something that, this is another solution that I probably should have mentioned on the previous slide. Sometimes this is done from the application, and scalable sequences basically just builds that into the sequence object. So you prefix it with a 6-digit numeric offset, and the offset is derived as follows. The first 3 digits is an instance offset. It's computed as the instance number modulo 100, and it has 100 added, which I'll talk about shortly. Then the next 3 digits is a session offset computed as the session ID modulo 1000. And now let's look at the significance of the, the starting digit always being 1. So let's look at 2 different offsets generated on the same instance. So let's say the instance offset is 0. This is ignoring the leading one. And if you have 2 different sessions with sessions offsets 0 and 100, then if one of the sessions returns uses a next val of 12, at some point the other session can have a next val of 10012, and without that leading 1, they're essentially returning the same sequence value, and this violates the prime property of sequences of always returning unique values. So scalable sequences can be defined in 2 flavors with the extend and the NOEXTEND keywords. The default property is the NOEXTEND, so we look at that first. So in a NOEXTEND scale sequence, all the generated values have the same number of digits as a maximum, as a number of digits in the max of the min val or the max val. So this means that the numeric scale prefix uses 6 digits from the existing sequence value space. And this is a very extremely important mode to ensure backward compatibility with applications, because we want to make sure that altering a sequence to be scalable is not going to break existing applications by generating values that are wider than what the application can consume. So for example, if you have a sequence with a max value of 1 million, then you're going to, such a sequence with no extent can only produce, assuming it starts with 1, that you can only produce 9 values from 1 to 9, because the max value requires 7 digits, and of the 6 of them are going to be used by the scale prefix. The second property is the index mode, is the extend mode, sorry. With the extend mode, as the name suggests, it's not going to use up digits from the sequence space. Instead, the prefix is added on to the beginning of the sequence value. So it basically is producing a much wider value. So this is more useful if your application is resilient to wider values, or if you're writing a new application, and you don't want to waste the sequence space, then you can use the extend flag. The syntax, I think we've already seen this as part of the earlier slide. So basically the extend keyword is optional. By default, it's no extend. Okay, the important point to note here is that when you alter a sequence with no scale, it basically disables scalability. However, if any scaled values were already returned, then we run the risk of generating a duplicate at some point, because especially if you use the NOEXTEND, if you remember, we're going to we were using the sequence space for generating values. So now that we've marked it no scale, as the sequence keeps incrementing, it could reach a point where you've returned, where you're incrementing the sequence into the space that was used by the prefix. So to avoid this, as soon as we mark a sequence no scale, we update the high watermark on disk with the largest possible prefix, just to ensure that anything you produce has to be greater than this. So the step clearly reduces the sequence space. So, you have to use some caution in altering from scale to no scale. And for obvious reasons, we don't recommend using scale with ordered sequences, because you clearly don't get ordering. By prepending the prefix, you've lost all ordering, but you're still going to be paying the high price of getting the SVNQ. Okay, so how do sequences work on an ADG setup? So ADG is basically providing read-only access to a physical standby when a redo apply is active. So when a sequence is accessed on the standby, we need to ensure that it is coherent with the definition on the primary, with the definition and the usage on primary, based on what cache of values is being used on the primary. And of course, we know that we won't be able to update the sequence high watermark on disk for the standby, but can we read and use the high watermark of the standby? We could, but it isn't as straightforward, because we have to make sure that the redo has been synchronized on the standby based on, you don't want to be using the same cache that the primary is still using. So to get around this, the standby always obtains a cache of values by making an RMI connection to the primary. So we never read the high watermark on the standby. And once again, optimal sizing of the cache is greatly going to help reduce the number of RMI calls made. Okay, this is just a small note on using sequences with parallel DML. You can update a table column with a sequence using the enable parallel DML hint. And this automatically splits the sequence cache between the specified number of parallel processes. The speed up you get is on account of, one is just the fact that you're using parallelism. And the second is that the parallel workers, once they partition the sequence cache and get their own, they basically are maintaining their own worker cache. And so, the values returned from there can be done even without the latch. So it's going to be much faster. Okay, then let's look at session sequences. Session sequences are defined with the keyword session in the create or alter sequence DDL. They're local to the session. So every new session will start returning values from the beginning, that is, from the sequence min value. Automatic restart every time you start a new session. And again, this is going to be really fast if you know that your sequence is restricted to your session, because you never have to make a trip to disk. By default, sequences are not session sequences. The keyword to mark it from session to a non-session sequence is global. Again, a global sequence just means it's a regular sequence that we're all used to. Now, the restart keyword was introduced in 18C. And this is a way of providing the restart, that restart capability that the session sequence demonstrated for the regular sequences as well. So if you just specify restart, it's going to restart numbering from the min value. And if you can also specify your start with and specify an integer. And the only restriction there is that it must not violate the min value, max value constraints, etc. Again, anytime you use restart, you're going to be there's a possibility that you're returning values that were already returned. So you have to be completely aware of this and, to make sure you're not breaking some constraints with your application. Okay, finally, how do we, I'm sure most people are, familiar with these tables. So basically, this is how you would monitor your sequence usage. For the sequence metadata, you can look at user sequences, and the corresponding all sequences and DBA sequences. With the features that we discussed today, you will see the scale and extend flags as part of these tables to tell you whether, they've been marked with, with those attributes. For sequences that are currently being used or being currently loaded, you can look at $v$ and the $GV$ sequences. So this view always had the cache size column, which basically tells you the user specified static cache size. And the new column that's added now is a dynamic cache size, which basically tells you at any given point what is the size to which the cache has grown. To trace sequence usage, you can see you can use the events shown here. Levels 1 to 5 are the different levels that you have. Level 1 is the lowest; it only traces the flow, and level 5 dumps everything, including the KGL object, locks, spins, waiters, etc. So on a production system, though, we would discourage using tracing even at level 1, because sequences are kind of like this, because this would turn it on for all sequences, and sequences are kind of fundamental to a lot of operations in the database, like right from startup. So you would not want to overwhelm the system with tracing. Okay, so that's all I have. And if there's any questions, I can discuss that. Looks like there are none.
Let's wait a little bit.
Okay.
People are okay. There is the first question.
Okay, yeah, I guess I used some Oracle speak. So this is basically the library cache object. So I don't know how I would put that as. So basically, it's just are you if you're familiar with the row cache, let me just put it this way. So tables on disk. So you have a cache defined on the table, which basically, you know, for each row on certain tables, it's like an in-memory kind of representation, you know, that's loaded and pinned. And the library cache basically extends that row cache a little bit. So the way I would define it is a loaded representation of a sequence in memory. So I hope that kind of answers the question. I think I refer to this in terms of keeping the KGL object in memory. So it's more like as far as sequences are represented are concerned, it's more like, you know, we've loaded a sequence once. You don't want to, you know, unless there's a DDL that changes the metadata representation, you don't want to keep reloading it. So it's a way of just keeping that in memory. Okay, for dictionary objects, is fine, but when it comes to applications, like especially, it is not practical to use cache and no order. I agree. So you should, ideally, we should not use cache. So no order, again, I think under no circumstance makes sense, because you can always have a cache size of 20, and you know, that's small enough that there's no reason, even if you're using the sequence very rarely, to go to disk. So yeah, so you're right that you would cache and no order. Yes, no order specifically means that the cache can never be used, because sorry, I think I got this all wrong. Order and cache and no order. Yeah, this is the most common situation, though. I think I'm confused by your question. Comes to applications like especially invoice, it's not practical to use cache and no order. Why would you say that? Is it because you always want it to be incrementing? As per law. So I guess maybe where there's a difference in the ordering as we view it as being returned from the database sequence object and how the application sees it. From the application perspective, I understand that, you know, you want every invoice or invoice number to be incrementing, which is, I think, why you're saying it doesn't make sense to have it cached, because you are losing ordering in some sense with the cache. So that kind of ordering would have to be enforced more from the application level. But if you were to enforce that right at the database level, that would make returning sequence values from the database object really slow. So it is still practical to use no order, get a bunch of values, but then use the one that makes sense for your application. The next question, is there any way the cache is not lost after restart? Unfortunately, no. So, however, if it is a failure, then there's no way to guarantee that you can't lose the cache. However, say you have loaded your cache with a huge cache size, say, you have 10K as the cache size, and you are turning down, shutting down the database yourself. In this case, because it's a clean shutdown, we do look at the last value that was returned, and we write that as the high watermark to disk. So you wouldn't lose the cache if it's a clean shutdown, but you would lose it if there's a failure. So this dynamic cache resizing should be available in the next version. Okay, that's a remote method invocation from the standby to the primary. I apologize. I'll make sure in future I keep this in mind when I'm making my slides.
See, questions are coming one by one.
Well, even if it's read-only, like I said, sequences are used in, you may be using it just, to, you may not be using it to write to a table, but you may be using it internally just, for some kind of ordering. And we've seen this in many cases. And so while you're not going to persist it on disk, you still want to make sure that, you can get a sequence value out. You can pretty much almost not bring the database up if you don't have sequences available. They're internally used in like throughout, I think.
So I think that's all.
Mm-hmm.
Yeah, no more question. Thank you so much for the presentation. Looking at the comments on the chat, people enjoy it, and it was excellent. Hopefully, we will have a chance to see you again with other topic.
Sure, thank you.
Thank you so much. Have a good day. All others have a good evening, and yeah, remember, another 3 days of the virtual tour are going on. Thank you. Bye bye for now.
Thank you all. Bye.